all the data structures and the abstract data types that we have investigated in this series so far are so-called linear data structures. So far, we looked at only linear data structures, right? Things like array and linked list and queues and stacks, right? And if you think about these data structures, there is an inherent order in the elements. That's why they're called linear. First element of the array, second, third, and so on. In a linked list, uh, at every node, you can talk about the next node. If it's a doubly linked list, you can talk about the next node and the previous node. So hence the name linear data structure. Today, we're going to look at a data structure that is not um, linear. Namely, we are going to look at trees, okay, which is not linear. Now, in this video, we are going to look at only definitions, and we look at the trees from the conceptual point of view. But these definitions are going to be used in the later videos when we actually implement things like binary search trees and balanced binary search trees and all of that. So this is kind of like the prerequisite for those videos. We cover all the concepts and definitions that we need in this first video. Now, the first thing I want to tell you about trees is that similar to linked lists, when we are going to implement them, there will be a linked structure as well. But obviously, it's not going to be linear in the sense that in a linked list, as I told you, you have either at every node only access to the next node or next and previous, depending on whether it's a singly linked list or a doubly linked list. Here, instead of talking about next and previous, we have a different kind of relationship between the nodes that I'm going to call ancestry. And the idea is that a node can be the parent of another node, a node can be a child of another node, or two nodes can be siblings and relationships like that. So we can talk about parents, children, descendants, ancestors, siblings, and such. Okay, and it turns out that as we will see in the later videos, this is going to be much more powerful than a linked list. And there will be, and there is actually a ton of applications of trees in computer science. We are not going to go into that much detail about applications, but for example, parse trees, if you've heard of that, that's one application that, a programming language parses your code and so on and so forth. Now, here's the only example, or the first example I'm going to give you in terms of the application is I'm going to show you something called an abstract syntax tree, or an AST. And the idea is that when you have some kind of text, it could be some text in a natural language, like in English, for example, or source code in any programming language. It may seem like plain text, but there is some kind of syntactic structure to the text, right? Like, the code nested inside in a block, and that block is nested in another block, and things like that, right? Um, and what is done is that this idea of a tree is used to represent this syntactic structure of some text. Again, when I say text, think of some mathematical expression or some source code in a programming language and so on. Okay, just to give you an example, look at this uh, mathematical expression. So 5 minus x times y plus 2, for example. right? Now, if I want to show, this is in linear form, right? This is how we write in mathematics or in most programming languages. But if I want to show the structure of this expression, I can use a tree to represent that. And multiplication will be on the top of that tree. And then the multiplication is a binary operation. So it has two operands, 5 minus x and y minus 2. So the left branch is going to represent 5 minus x, and the right branch is going to represent y plus 2. And 5 minus x itself is a mathematical expression. The operation is subtraction, so that goes there. And then the left operand for that is the constant 5, and the right operand for that is x, the variable x. Similarly, on the right side, y plus 2 plus is the operation. It's a binary operation. On the left side, it has the variable y, and on the left side, it has y. On the right side, it has the constant 2. Okay, so this tree, which happens to be a binary tree, which we will define in the next video, is a representation of this arithmetic expression using the tree structure. Now, as I said, the focus here is going to be mostly on the definition, terminology, and all of that. So let's move on from this example and talk about some of the things that we're going to do in terms of concepts and definitions. Okay, now elements in a tree, like for example, here we have multiplication, minus, plus, and so on. These are called the nodes of the tree or vertices of the tree. So nodes are going to be elements in a tree, and we are going to represent them with circles from now on. So something like this. And then if there is a value in that node, I write that inside the circle. Sometimes I label them so that we can have a name for each vertex and talk about them, right? So that's the definition of a node or a vertex in a tree. And then, as I said, a tree is a linked structure. So these are the links, and the technical term for it is an edge. So an edge is a connection between two nodes. So each connection between two nodes is called an edge. And at the beginning, I'm going to represent an edge with an arrow. But later on in this video and for the rest of the series, I'm going to replace the arrow with a straight line because the direction will be clear based on the way that we draw the trees or the trees. So to give you an example of nodes and edges, here's an example. So imagine that you have a tree that has A here, and then on the left it has B, on the right C, and B goes to D here, and C goes to E and F. Okay, so this is a tree that has the number of nodes or vertices. It has 1, 2, 3, 4, 5, 6 nodes, and the number of edges, the connections between the nodes, is 1, 2, 3, 4, 5. Okay, now for all of this, what is a tree, what is an edge, and all of that, there are rigorous mathematical definitions, but I don't find them very useful in the context of data structures, going through all those formal definitions. For this series, if this was a course in graph theory, I would give you the formal definition of all of this. But here, having an intuition about all of this is much more useful and less confusing than the formal definition. Now, one thing that I want to tell you right at the beginning is that not every diagram or graph like this with nodes and edges between them is going to represent a tree. For a graph like this to be a tree, we need to have two conditions. The first one is that all the nodes must be connected. Now, again, connected is one of those concepts that there is a mathematical definition for it, a formal definition, but informally, which is good enough for us here, it means that for every two vertices every two nodes that you choose, there should be a path from one to the other. Okay, there should be a way to get from every node to every other, ignoring the directions. So from D to C, for example, you can go to D to B and B to A and A to C, right? And so on and so forth. If there was more vertices, more nodes like G and H here, this entire graph uh, wouldn't be a tree anymore because there is no way to go from G to A or from B to G and so on. So that wouldn't be a tree because it's not connected. So that's the first condition of a tree. The second one is no cycles. Okay, now an example of a cycle, imagine that you have four nodes like this, A, B, C, and D. Okay, now if I add an edge here between B and C, then I have a cycle here from B to A to C to B. That's a cycle, and that is not allowed in a tree. Or another example would be something like this. Yeah, from here to here, for example, right? Again, and let's say there's another one here called E. Okay, again, here we have a cycle from A to C, C to D, D to B, and back to A. And because there is a cycle, this is not a tree. So no cycles, and every two vertices are connected. Okay, so that's the definition of a tree and also nodes and edges. Um, now, before moving on with next definitions, I want to talk about some special cases. So the smallest kind of tree that you can imagine is a tree with no node or no vertex, which is usually called an empty tree. And the representation is just empty. There is an empty there, right? Now we can have a tree with one node only, okay? And it's going to look like this. And you may want to give it a name, A, but there is no edges because there is no second node to connect them to each other, right? So that's a tree with one node. And then, of course, you can have a tree with two nodes, three nodes, and so on. So a tree with two nodes looks something like this. So you have a node called A and another node called B, and then you connect with an edge. Okay? And then trees with more nodes obviously are possible as well. Okay, now back to the definitions. The next definition is the definition of root or a root node. Root node. Okay, the root of a tree is a node that doesn't have any incoming edges. So a node with no incoming edge is called the root node. And usually we draw that on the top of the tree. So the top node usually represents the root. So for example, if this is your tree, A, B, C, D, E, and F, and you realize that I didn't draw the arrows anymore. I just used solid lines. So A, technically the arrows would be like this, right? A, if you look at A, it has two outgoing edges, but there is no edge coming into A. So A is the root of this tree. Okay. And the reason that from now on, I'm not going to draw the arrows anymore and just use lines to connect the vertices is that the convention is the edges are always directed from top to bottom. And that's why I said that the top node is always the root of a tree. That's the way that we draw them. Okay, so that's the root. Another example would be a tree with only one node, just like that. Again, that only node is the root. And if you have two nodes, then again, this one is the root. Okay. And we are going to assume that, and this is a good assumption in the context of data structures, we are going to assume that all the trees that we are going to work with are going to have a root. Okay. So that's the definition of a root. Next definition, remember that I told you about the relationships between the nodes. I told you that the node can be the child of another node, and that node will be the parent of this node. So let's define that. So a child node has a line or an edge down from its parent. So in the same sentence, I'm defining both the meaning of the child node and the parent, right? And I should say here directly. Okay. Now, what do we mean by that? Let's take a look at an example. So here's my graph. Here's my tree. A, B, C, D, E, and F. And let's say here G. Okay. So if I want to give you some examples of this relationship, for example, there is a line directly from A to B. So we say that B is a child of C. I'm sorry, B is a child of A, or we say A is the parent of B, right? Similarly for C, C is a child of A, so A has two children, B and C, and C has A as its parent. C itself has three children, so D is a child of C, E is a child of C, and F is a child of C, and C is obviously their parent. And G is a child of B, which means B is the parent of G, right? So that's the child-parent relationship. So if you think of this as a family tree, then it's very intuitive. The only difference is that in our trees, every node, except the root, because the root doesn't have doesn't have a parent, but every other node, if you think about it, has exactly one parent. So C has A as its only parent, B has A, and so on. So that's the child and parent nodes. Another definition is the definition of a leaf node or a leaf. And the definition says a node is called a leaf if it doesn't have any children. So a node with no children. Okay. Now, if you think about it, if you look at this graph here, the leaf node or the leaves of this is a leaf. G doesn't have any children. D is also a leaf. E is also a leaf, and F is a leaf. So this tree here has 1, 2, 3, 4 leaves, 4 nodes where each one of them has no children. Okay. Now, a definition that accompanies this is what's called an internal or interior node. An interior node is a node that is not a leaf. So a node that is not a leaf. Okay, so in this the tree here, G, D, E, and F are leaves, which means that A, B, and C are internal nodes or interior nodes. Okay, so a lot of definitions, and we are going to use these later on when we work with trees as data structures. Now, before making a couple of more definitions, I want to make a couple of very simple but important observations. The first one, as I said, is that every node except the root has exactly one parent. So every node, every vertex, except the root node, has exactly one parent. Okay, and the second observation, which is also obvious, is that a node can have as many children as they want. A node can have 0, 1, 2, or more children, right? So if you look at this example here, A has 2 children, B has only 1 child, C has 3 children, and G, D, and E have 0 children, right? So, and it's possible that, C has like 4 or 5 or 10 children as well. So there is no limit, unless we talk about what's called binary trees, which we will talk about in the next video. In that case, we limit the number of children to either 0, 1, or 2. Okay. Two simple, very basic observations. Now, my last two definitions, I mentioned them briefly at the beginning when I was talking about the possible relationships between the nodes. The first one is the definition of an ancestor. So the ancestor of a node is either the parent of a node, or the parent of the parent of the node, or the parent of the parent of the node, and so on and so forth. So that's the definition of an ancestor. And then the opposite of that is the definition of or the relationship of descendant of a node. So we call a node a descendant of another node if it's either the child of that node, or the child of the child of that node, or a child of the child of a child of that node, and so on. Okay? And it's best if we investigate these in an example. So here's my example. We have A on the top, B and C, and then we have, let's say, here on this side, we have, and I'm just naming these randomly. The order is not important at this moment. So D, E, F, and B goes to, say, H on this side, and G on this side, and finally, G and I as a child. Okay, so we can review everything that all the definitions that we introduced so far, and then also talk about descendants and ancestors. So let's start with the first definition: the number of nodes, the number of um, edges. So the number of nodes: 1, 2, 3, 4, 5, 6, 7, 8, 9. The number of edges, the connections, is 1, 2, 3, 4, 5, 6, 7, 8. Then we had root, or the root node. In this case, that's A. We had leaves, right? In this tree, I is a leaf, H is a leaf, D, E, and F. These are the leaves. So 1, 2, 3, 4, 5 leaves. So this tree has 5 leaves. Now, the child-parent relationship, there are many of them. But let's talk about ancestors and descendants. So if I want to list all the ancestors of, say, I, so we have G, which is the parent, and then the parent of G is B, and the parent of B is A. So I has G as its parent, B as the parent of the parent, and A as the parent of the parent of the parent. So G, B, and A are the ancestors of I. And if you want to talk about, say, descendants of, for example, B, then that would be the children of B, which means G and H, and their children, which means I, right? So everything below B will be its descendant. Its children, the children of the children, or grandchildren, and then great grandchildren, and all of that. Right. So that's the definition of ancestors and descendants. in a tree. Again, very similar to a family tree. And finally, we can also talk about siblings. And let me write that down as the final definition. We say two nodes are siblings if they have the same parent. So that's the final definition. Two nodes are siblings if they share the same parent. Same. Okay. And going back to this example here, for example, we can say that uh, D, E, and F are siblings because C is the parent to all three of them. So D, E, and F are siblings. Similarly, G and H are siblings because B is their parent, and B and C are siblings because they share the same parent, which is called A. Okay, so that's the fundamentals or very basic concepts and definitions. Then we talk about trees. I didn't go into full mathematical rigorous definitions because that would be more confusing than helpful. Uh, and we want to talk about these concepts at the right level that is appropriate for our application, which is using trees uh, for our data structures. Now, the main two things that defines a tree is that a cycle is not allowed, and also the graph must be connected. It means that between every two nodes, there must be a path. Like, for example, between G and C, there's a path that goes from G to B, B to A, and A to C. And since there's a path between every two nodes that you select from this, we say that it's connected, and obviously it doesn't have a cycle, and that's what makes a tree. And then we have the definition of a root or root node, uh, and parent, child node, siblings, ancestors, and descendants, and finally leaf nodes or leaves, which are nodes that have no children. In the next video, we are going to look at the special case where we limit the number of children of every node to at most two, and that's what's called a binary.